Hello, and welcome. Have you ever stopped to notice the rhythm of the world around you? The gentle, repeating pattern of waves lapping at the shore. The steady, predictable swing of a pendulum in a grandfather clock. The familiar cycle of day turning into night, and night turning back into day. These patterns are everywhere, from the smallest atoms to the largest galaxies. They are the heartbeat of the universe. And today, we're going to learn the language to describe them. We're going to explore a simple but profoundly important concept called periodic time. Now, I know periodic time might sound like a phrase straight out of a heavy physics textbook, but I promise you, by the end of this, you'll see it's an idea you already understand intuitively. We're just going to give it a name and a clear definition. Let's look at the information on our screen. The title is clear: periodic time. Let's break that phrase down. The word periodic simply means something that repeats over and over again in a regular, predictable interval. It has a period, a cycle. Think of a weekly magazine subscription. It arrives periodically, once every week. The seasons are periodic, repeating their cycle once every year. And time, of course, is just what it sounds like. We're measuring how long something takes. So, when we put them together, periodic time is about measuring the time it takes for one full repetition of a pattern. Let's look at the formal definition on the screen. It says, the time it takes to complete one cycle of the wave is called period. Let's carefully dissect this sentence. The first part, the time it takes, tells us our primary focus is on duration. We're asking how long? We're essentially starting a stopwatch. The next part, to complete one cycle, is the heart of the concept. What exactly is one cycle? A cycle is a single, complete performance of a repeating event. Imagine a child on a swing. One full cycle would be the child starting at the highest point, swinging all the way forward, then all the way back up to that same starting height. That entire journey is one cycle. Once they complete it, they are ready to do the exact same thing again. And the last part of the definition is of the wave. Why a wave? Because a wave is the beautiful, universal picture we use in science to represent almost any kind of periodic motion. That smooth, flowing line on the screen could represent the changing pressure in the air that our ears interpret as sound. It could be the rise and fall of the tide. It could be the oscillating electric and magnetic fields that we see as light. The wave is our visual tool for understanding these repeating patterns. The next sentence tells us, it is denoted by T. In science and mathematics, we like to be efficient. Instead of writing periodic time or period over and over, we use a simple symbol as a shortcut. That symbol is a capital T. So, whenever you see a capital T in discussions about waves or vibrations, you can confidently say, that's the period. That's the time for one full cycle. And finally, unit of time period is second. Every measurement needs a unit. If I say the distance to the store is 5, you don't know if I mean 5 feet or 5 miles. It's the same with time. The standard scientific unit for time is the second. So, if a wave has a period of t equals 2, we mean it takes 2 seconds to complete one full cycle. Of course, periods can be incredibly short, measured in nanoseconds for light waves, or incredibly long, measured in years for planetary orbits, but the second is our fundamental building block. Now, let's bring this to life by looking at the graph itself. This visual is where it all clicks together. Imagine the horizontal line at the center is the rest or equilibrium position. The line itself, pointing to the right, is labeled time. As we move from left to right along this line, time is passing. It's our timeline. The vertical line represents the quantity that is oscillating. It could be the height of a swing, the pressure of the air, or the strength of an electric field. Let's trace the journey of our wave, starting from the very beginning, at time 0. The wave starts at the center line and begins to move upwards. It climbs and climbs until it reaches its highest point. This peak is called a crest. Then, it's pulled back down. It crosses the center line and keeps going. It moves downwards until it reaches its lowest point. This valley is called a trough. But the cycle isn't finished yet. To complete the cycle, it must return to its starting state. So, it moves back upwards, finally reaching the center line again, ready to start the next identical journey upwards. This entire sequence, from the start, up to a crest, down through the center, down to a trough, and back to the center, is one complete cycle. Now look at the bright cyan markings on the diagram. They perfectly capture this. The large bracket spans the exact portion of the timeline that our wave took to complete this one cycle. It's labeled one cycle. And what do we see labeled right underneath that bracket? Our symbol, T. The diagram is visually telling you, the length of time on this timeline that corresponds to this one full cycle is the period, T. But here's something incredibly powerful about this concept. You don't have to start measuring at the beginning. The period is consistent. You could start your stopwatch at the very peak of the first crest and stop it at the very peak of the second crest. The time that passed between those two identical points would also be exactly T. Or you could measure from the bottom of one trough to the bottom of the next. Again, the time elapsed would be the period, T. The pattern is regular, so the time for one full pattern is always the same, no matter where you start measuring. Now, let's introduce a twin concept that is inseparable from period, frequency. If period, T, answers the question, how long does one cycle take? Frequency, which we denote with a lowercase f, answers the question, how many cycles happen in 1 second? They are two sides of the same coin. A long period means a low frequency. If a wave takes a long time to complete a cycle, not many cycles can fit into 1 second. A short period means a high frequency. If a wave is very fast and completes its cycle in a tiny fraction of a second, then many cycles can fit into 1 second. This relationship is beautifully simple, T equals 1 divided by f. The period is the inverse of the frequency. Let's make this real with some examples. Think of a deep, low note from a bass guitar. That's a sound wave with a long period and a low frequency. Now think of a high-pitched note from a flute. That's a sound wave with a very short period and a high frequency. The colors we see are just light waves with different periods and frequencies. Red light has a longer period than violet light. The electricity coming out of your wall socket is alternating current. In North America, its frequency is 60 Hz, meaning it completes 60 cycles every single second. Its period, T, would be 1/60th of a second. So, as you can see, this simple concept shown in the image, the time for one cycle, is a fundamental key. It helps us understand and describe the world of sound, light, electricity, and motion. It's the rhythm, the tempo, the very pulse of the physical universe. So next time you hear a sound, see a color, or even just feel your own heartbeat, you can think to yourself, that has a period. And now, you know exactly what that means.